I'm a professor at DTU Compute. I also coordinated a similar center, but related to industrial IoT. And now this has become a Nordic University hub on industrial IoT. So I'm very happy to talk to Roberto and the other guys about what it means to run a center and involve researchers. And I really like the current event and how things are shaping up. I'm a computer scientist, and I'm going to tell you a few things about vehicle architectures and how you have to design them and configure them in order to make them more dependable. So I'll tell you a few things about the evolution of these electronic vehicle platforms. What are the challenges related to dependability? Some of these, the big picture has been covered by the previous speaker. Then I'll give you some examples on how this architecture look like in terms of computation, communication. I'll give an example configuration problem, and if there is time, I can go through some projects that we have at DTU Compute related to autonomous systems. So autonomy in many things, in robots, in vehicles, and so on, is realized through a combination of hardware and software. And software has been increasing in complexity. Here you see the increasing complexity of automotive software. It started actually with analog devices in the 70s used for fuel injection and anti-lock brakes. And then in the 80s, and in the 90s, we had things like power steering and stability control. And a lot of the things that are now driving the complexity have to do with some degrees of autonomy. And you have probably seen, and this is increasing exponentially. We have more and more software in vehicles and more hardware. You have probably seen, I don't know if today, but these 6 levels of autonomous driving, from no automation, I think very few cars have no automation today, to full automation, which is the holy grail. But there's also a lot in between. And cars nowadays actually have a lot of autonomous functions which are at the lower levels. I'm going to focus on level 1 and level 2 in terms of driver assistance. But there are applications, and one of the applications that we looked at is where you have full automation, for example, lateral parking, where you don't touch the wheel, the car will park itself. But of course, the risk there is reduced because you're not at high speed on a highway, you're just parking the car. So we have this increased functionality due to increased autonomy. And we have many functions, things like adaptive cruise control, where the car uses radar to keep a constant distance from the car in front. We have lane departure assistance, where you will be warned if you're trying to change a lane, but there is another car that you don't see, or if a car is coming to your lane. Blind spot assist, car may also brake automatically, for example, if there is somebody quickly stopping in front of you. All of these applications are real-time and safety critical. Real-time means that they have deadlines. That is, the correctness of the functionality depends not only on the results of the computation, but also the time when these are delivered. And for example, an adaptive cruise control will have to compute everything and read data from sensors, take decisions, and apply commands to actuators within, for example, 100 milliseconds. And if it does later than that, then some catastrophic consequences may occur. These are also safety critical. The previous speaker has discussed about safety. Many of these systems may harm the human life or the environment if they malfunction. And dependability here is not only about safety and fault tolerance that is needed to operate even in case things fail, but also about security and privacy. There are demonstrations of how people have taken, how researchers have taken control over cars on the highway, and they could control the car, for example. And this is also changing the way we develop these electronic architectures for vehicles and how we configure and design the software for them. What we see currently is such a picture where you have multiple networks with over 100 ECUs. An ECU here stands for electronic control unit, is a processor, could be a multiprocessor. with some memory and communication. And they are currently implemented in multiple networks in a vehicle. So you have, for example, a FlexRay network if it has to do with the powertrain, a CAN or controller area network if it has to do with the engine or with other body functions. So several types of networks with over 100 such microcontrollers connected to each other. This is what you have currently in vehicles. And the different networks target different types of functionality depending on how, let's say, tight are the requirements. If it has to do with maybe controlling like windows and the dashboard, then the demands are not so high. And then you use a local interconnect network with some ECUs that are not so powerful. If it's about the engine or the stability of the car, then you have maybe other types of networks like FlexRay and more powerful multi-core processors. What we see as challenges is that we have this rapid growth of software functionality that I mentioned, and we simply don't have enough computation performance. There are a lot of ECUs, but they are not powerful enough. They don't have enough memory. And we cannot address functions like autonomous driving, connectivity, infotainment, electric cars, hybrids, and new mobility requirements and cooperative functions with the current architectures. So what we see is that we go from these distributed separate ECUs, and which each of them may be connected to some sensors like cameras or radars, and you have to find some space for them in the car. So you have a separate ECU for each type of function. If you have, for example, something to help you with collision avoidance, maybe you have one ECU for that. If it has to help you with lane keeping, there is another ECU for that, each with its own hardware. With its own software, for example, for doing image processing and so on, and connected to these sensors. So the trend is now from you go from these separate ECUs to more integration, where you have more powerful centralized computing inside the vehicles. There is now a trend in computation called edge computing or fog computing, where you have a lot of data center and cloud computing capabilities that are coming close to the edge of the network. You see the same things for vehicles. You concentrate some of this computation power into what looks like a data center on wheels, looks like edge computing or fog computing on wheels. So you have more powerful hardware. I'll show you some examples. You can handle then more software, more complexity. You connect to a lot of these sensors and actuators, and then you have implement these high-level functions using your software. So this is the trend today. And in terms of advanced driver assistance systems, ADAS, these are some of the sensors that are needed. I will not go into detail. So there's a lot of sensors. What is important here, so from radars to lidars to cameras to short-range radars, ultrasonics, and so on, the message here is that you have a lot of data coming into the cars from a lot of sources. You have, for example, videos or LiDAR coming in information. And this is a huge amount of information compared to what cars had to process before. Maybe cars were concerned before with things like the speed of the car and maybe to adjust something related to the fuel injection, maybe a few bytes of a message exchanged within the car. Now suddenly you have video that you have to process and you have to communicate within a car. And current architectures cannot handle this amount of data. And that's why we also have new types of communication architecture in vehicles, and I'll mention those as well. And all of these radars are needed to implement these functions that are there on the right, like from adaptive cruise control to traffic sign recognition and blind spot detection and so on. If you want to have if you want to see how these sensors look like, they look like something like this, and there's a lot of them in the cars. You have, for example, stereo cameras which are on top of the windshield. You have a lot of environmental cameras to the sides of the cars, maybe a front camera, radars, lidars, different sizes, scanners, and so on. And in terms of hardware, you don't have to read all the text here. There are companies now, for example, this is a platform called Razer Motion from two companies, Renesas, which is a hardware developer, and TD-Tech, a collaborator of DTU Compute, a company in Austria. who are developing this integrated, let's say, ECUs with a lot of capabilities, with a lot of processing resources, a lot of multi-core processors, maybe even GPUs for processing video, all sorts of specialized systems on chip with interfaces to video and towards the sensors, for example, interfaces, and also communication interfaces for within the car. So this is how such an integrated platform may look like. And if you look at the software platform, the software stack, this becomes quite complex because you have multiple multi-core processors. You may have systems on chip with multiple cores, some GPUs, and they run different operating systems. Some of these operating systems have to implement real-time safety critical functions, so they are safety real-time operating systems. Some of them are for more legacy automotive functionality, like AutoSAR, for example, which is an operating system in automotive. And then on top of these many operating systems, you also have operating systems like Linux if the functions are not safety critical or not real time. On top of it, this you have middleware that is allowing your processes, they are called tasks in real time speak, in real time theory, they allow your tasks to execute, and you have to execute them using some specialized scheduling policies that can provide guarantees that these tasks will fulfill their timing requirements, and all sorts of other requirements. There are many requirements. Imagine, for example, you have a lot of what is called chains, dependency chains from reading from a camera or multiple cameras, moving this information on the network to a centralized computation unit, executing these tasks to maybe some tasks on the GPU to do image processing, executing tasks, and to take the decisions, and then applying those decisions to actuators, maybe to the brakes, to the throttle of the car, and so on. And this is also then connected within the car itself via a backbone. For example, a trend now is in vehicles is to start using some Ethernet variants. I'll tell you about that in a moment, because those are the only ones that have enough bandwidth to run, to disseminate all of this information within a vehicle. Now, if you look at and what the point here is that these are, as you see, quite complex platforms in terms of hardware, software, operating systems, middleware, a number of tasks. There are thousands and thousands of tasks that have to execute here. And it's very challenging to design this platform. When do you have enough computation power? And it's very difficult to configure them, because you have to decide, for example, where should the tasks execute, for how long, how do you schedule these things, and so on. And this actually has become an intractable optimization problem, which is very difficult to solve. We collaborated, I'll show you in a moment, with automotive manufacturers to solve these problems, because they don't have good solutions on how to configure these things and to guarantee timeliness and safety criticality at the same time. In terms of connectivity, the trend is that wiring, point-to-point wiring harness, like you see here on the right, has been slowly replaced with multiplex networks in vehicles. It got to the point where just this wiring harness in a vehicle had a weight which was more than the engine, and it had cost which was higher than the engine cost. So it was then replaced with multiplex networks such as controller area networks, CAN, and also specialized protocols for vehicles like FlexRay. But even those protocols nowadays, they cannot handle the amount of information that is disseminated within a car and in collaborative vehicles. So we use, so the trend is now towards network convergence using a variant of Ethernet, which is called time-sensitive networking. This is basically a standardization effort at the level of IEEE, which is extending Ethernet, that you all know, with substandards that provide real-time and safety-critical functionality, making sure that things work even if you may lose some messages, making sure that you can actually have traffic on the network that is very that has very tight requirements in terms of latency and jitter. So even you have a global notion of time here to have some synchronous traffic going through the network. At the same time, coexisting with standard Ethernet traffic or streaming traffic, for example. And then you use this Ethernet to connect the different ECUs here that each run different applications that then communicate via this Ethernet backbone. And there are now vehicles on the market that are using variants of this deterministic Ethernet, and this will be in future vehicles everywhere because it's a standard and it's well suited for autonomous functions because it can handle a lot of data in a timely way. Future vehicle architectures will look like this, where you have maybe different domains. For example, the powertrain domain here to the top right, where you have maybe something like CAN, maybe some more specialized CAN that can provide more bandwidth. And they have a domain gateway to a switched Ethernet network that is providing the backbone to communicate a lot of data, especially from cameras needed for driver assistance. More and more, the switch Ethernet will be used in more domains inside the vehicle. Now, I don't know how much time I have. I think I started a little bit later, 30 something. Okay, I'll try to end in a couple of slides because I think we're also delayed. So what you see here is an example configuration. This is what you need to plan in order to run all of these ADAS functions. So you have to decide for each core and for each multi-core processor on each core on each GPU, how are you going to run these tasks? Each of these color rectangles are a task that is running. There's also communication among them. You have thousands of these tasks, and you have to decide typically a static schedule because these are used in safety critical systems. Before you actually put the car on the market. So you have to decide where to place the tasks and how to schedule these tasks. And this is an intractable optimization problem for which you cannot obtain optimal solutions. So what we do, I'm a computer scientist, I design algorithms that help you to come up with such a solution that you see on the screen that meets all the timing requirements, and you're sure that it will not fail, for example, if you deploy it in vehicles. And this is an example work that we have done. We just got the Best Paper Award at on the Emerging Technologies track at the conference on emerging technologies and factory automation. Exactly on this, on mapping and scheduling automotive applications on ADAS platforms. And we use their meta-heuristics, which is a type of solution algorithm that can be applied to multiple problems. Okay, and these are some example projects, but I will not go into that, so I'll stop here. And any questions from the audience?
Okay, thank you very much, Paul. The floor is open for questions. Please, Morten.
Thank you, and thanks a lot for a really interesting presentation. My question is that in the public domain, the vehicles that comes with a long history and has ended up in this architecture for, amongst others, historic and specific reasons from that industry, they will meet the small industrial robots that comes on the sidewalk that we heard previously. I'm curious about the architectures of the, you can say, the old school vessels and the new class vessels. How do they relate, and should they reconsider, and what are the differences between the architectures of the different systems? Is the question understood?
Yes, thank you. In the vehicle area, these architectures are driven by cost. So because you are hoping, automotive is a mass market, and because you are hoping to sell a lot of vehicles, millions of vehicles, even if you can save 1 krona out of your architecture in terms of unit costs, this is millions and millions of kronas over time. So that is driven by costs, and in the automotive area, they were quite. It was quite an interesting development in terms of safety. They wanted not to have functions that are very costly in terms of safety, like you have in avionics. Of course, and then they have a lot of backup systems, like mechanical or hydraulic backups, which are avoiding putting more electronic and software functionality that would increase costs and which would increase, let's say, the risk. So they reduce risk by using backup systems like mechanics and hydraulic. Now, what you see in other application areas like small robots, what is happening there is that you have architectures that are coming from consumer electronics, which are especially designed to be extremely cheap and to have a high average case performance. And in many areas like automotive, where the risk is high if you crash, you cannot use such consumer electronic architectures because you don't know much about how they fail. A lot of them have a very short lifetime, and you don't have a good worst case performance. The average case performance is excellence, but the worst case performance is sometimes difficult to understand. This is even more pronounced in aerospace, but it's also so in vehicles you have specialized microcontrollers from companies like Infineon and Bosch and so on that are not very useful for smaller robots and for other application areas. Where there you go then with more off-the-shelf microcontrollers that are using consumer electronics because they are very cheap and very powerful. I don't know if this has answered the question. I'm not an expert on robots, but I see my colleagues, both at DTU Electro and in Denmark, using typical off-the-shelf architectures, and then something like ROS, this robot operating system, which has some other problems related to safety and so on, but that's what I see.
Thank you so much for the answer. It did answer a lot of it, and I think my end comment was that the two categories of vehicles will meet and overlap at some point. It's just interesting that they will come from such different backgrounds, and I think that's an interesting development area.
Yes, thank you.